Hello everyone. So in this video, we'll be looking at the connection between finite automata and regular expressions. Namely, we're going to see that any language that's accepted by an FA can also be denoted by a regular expression. And so the way that we're going to do that is that we're going to present a conversion algorithm that takes any FA M, so it can be a DFA or an NFA, and converts it to an equivalent, right? So using some algorithm, converts it to an equivalent regular expression, R, in the sense that L of R will equal L of M. Okay, so how do we actually do that? Well, we need to talk about something called a generalized transition graph. So a generalized transition graph is very similar to the transition graphs that we've seen for NFAs and DFAs, except that now edges can be labeled by regular expressions. And so all that means is that if the machine is at Q0, to transition from Q0 to Q1, what the machine can do is it can read any string that matches the regular expression labeled on its edge. Okay, so that's the real difference. That's the only real difference between a GTG and the transition functions for FAs, is that now we can label the edges of GTGs with regular expressions. And so transitions execute if the graph, or if this generalized machine reads any string that belongs to the language denoted by the labeled regular expression. Okay, so why is this useful? Well, to convert an FA to a regular expression, GTGs are actually crucial, okay? Because essentially they're this new data structure that allow us to keep track of the um, the mechanism of the machine while reducing the machine so that it becomes more apparent what the regular expression equivalent to it is. Okay, so that's exactly what the role of the GTG is. So the role of the GTG is to allow reducing the FA to a form where the regular expression is obvious. Okay, so in fact, the goal in this procedure of converting an FA to a regular expression is you start with some machine M, okay, and you convert this to subsequent GTGs until you get something that looks like this, okay? So this is your goal. This is your goal or your target, is you want to get to a machine that looks like this, where these labels on the edges are regular expressions, okay? Why do you want something like this? Because once you have a machine that looks like this, okay, now let me just relabel these just so it's clear. So let's say these are regular expressions, A, B, C, and D. So if I have a machine that looks like this, I can determine what the equivalent regular expression is just by reasoning logically about the transitions, right? So all of the strings that are accepted by this machine have to end in the final state. So how can you end in the final state? Well, you can read any string that's represented by A any number of times, okay? Then at some point you transition with D, okay? And then you have two choices. Either you stay in C, you stay in QJ by perhaps reading a C or perhaps by doing nothing, or you go back to QI with reading a string denoted by the regular expression B, perhaps staying in QI by reading strings from the irregular expression A, and then going back to Qj by reading a string denoted by the regular expression D. Okay, so saying a string denoted by the regular expression, let's say A. So this is the proper way of saying it, but because this takes a lot of words to say, and because it can be equally as well understood by reading A, right? I'm just going to say reading A. Okay, so reading. So if I say reading a string denoted by some regular expression, I can equivalently mean, in this case, reading A, the regular expression, okay? It's just going to make my descriptions of things a lot easier, a lot less verbose, right? So now if we go back here, the regular expression that's equivalent to this machine is going to be the regular expression that denotes the pattern reading A any number of times, then reading a D to get to Qj. So right, reading A any number of times, then reading D to get to Qj. And then you have the choice, right? You have the choice to either stay in Qj with C or go back to Qi by reading B, then staying in Qi for a bit by reading A any number of times, and then going back to Qj. And then you can switch between choosing this option and this option any number of times, right? In particular, this can be 0, right? So you can choose not to do any of these two things, and just read any number of A's and then D and then get to Qj. Okay. So the idea, right, the goal in the conversion algorithm is convert the FA to a GTG such that you have a single final state, which should be distinct from the initial state. So this is just an additional rule, because what you want is you want your additional state to be distinct from your final state. Okay. You're going to start removing intermediate states, and we're going to see how to do that. And you're going to repeat removing these intermediate states until you get this form. Okay. Okay, so now we're just going to do this in a bit more detail. Let me just take a sip of tea. Okay, so a more detailed explanation of the algorithm. So the first thing you want to do, you want to convert the FA you have to an FA with a single state as the final state. So how you can do that, imagine you have a bunch of final states. Well, you can convert these to regular states, so non-except states, and then create empty string transitions to a final state. Okay, so that's how you can do that. The other thing is you don't want the single final state to also be the start state. So you don't want something like this, okay? Because although you can sort of reason about similarly, we want a procedure that always works, and we don't want to sort of rewrite it for a bunch of edge cases. So for something like this, we want to make the start and final state distinct. And so we would want to convert this to say something that looks like the start state, then the empty string, the single final state, and then we have on the side the actual mechanism of the machine. Okay. Okay. So like I said before, the goal is to get to a GTG that looks like this. If you don't have this, then you have to start removing states. Okay. So how do you remove states? Essentially, you need to take out all states that are not the initial state and the final state. Okay. So for instance, here I have Qi, Qj, Qk. I want to remove Qk. So I want to remove Qk, but I want to keep all of the information from this graph. I want to preserve that information when I convert it to this smaller graph. And so how I can do that is that I can preserve the information of this graph, which is actually what transitions are allowed, by taking what transitions are allowed in this machine, converting those transitions to regular expressions, and then placing these regular expressions additional labels on my edges, okay? So that's the whole idea. The whole idea is you want to preserve the information of the transitions, right? So by information, I mean, where do you start? What do you read to get to where you are, right? So all the mechanisms of the transition functions. Preserve the information of transitions through state QK that you're deleting, state QK that's being deleted by representing the transitions with regular expressions and placing these new regular expressions onto the edges of the reduced GTG, right? So what I mean by that is if I delete QK here, I need to still preserve the fact that QK allowed me to get from QI to QJ, right? So it allowed me to get from QI to QJ by reading RIK, then reading RKK any number of times, and then reading RKJ, right? So that means that to preserve this information, it means that what I want to do is I want to say that to go from QI to QJ, either I can use this direct path, or I can use this other intermediary state, and then to represent choosing this other intermediary path, or by choosing this other path with this intermediary state, I represent the transition by a regular expression RIK, RKK star, RJK, and I take this, which represents the transition from QI to QJ through QK, and I place it on the edge that goes from QI to QJ, okay? So that's why now I have this on the edge from QI to QJ, because it's saying that now that I've deleted QK, I've preserved the information of what QK was doing. Namely, it was allowing me to go from QI to QJ using a transition that looked like this, okay? And so you repeat this, right? So the idea is to repeat, right? To repeat until you get a GTG that has this form, and then at that point, you can just write down the regular expression, okay? So now, because this is very fresh in your mind, let's quickly look at an example. So we want to find a regular expression that denotes the language accepted by the following NFA. Okay, so this is my NFA. So the first thing I do, I need to have a single final state, which has to be distinct from the initial state. Here, that's good. I have a single final state here, and it's distinct from the start state, which is denoted by 1. Okay. Okay. Now I have to convert this to a GTG. The only thing that I really need to do is, for instance, this guy here. This is saying that I can transition from 1 to 2 by reading an A or a B. So that's how I'll label this edge. Okay. So now I have a GTG. Now I'm going to just start removing transitions, or I'm going to start removing states. So I'll pick the state 2 to remove first, right? So if I want to remove this state, so I want to remove 2, I need to determine what 2 allows me to do. So what is it the intermediary vertex of what path? So what paths go through state 2, essentially, right? That's what I want to see. And then I want to preserve this information by adding these transitions to the new edges in my reduced graph, okay? So in what way does 2 act as an intermediate state? Well, we can see here that 2, okay, allows 4 to get to 3 by reading B, any number of B's, and then A, right? So to go from 4 to 3, I can use 2 by reading a B, then by reading any number of B's, and then by reading an A. The other thing that 2 allows me to do is that it allows me to go from 1 to 3, right? So it allows me to do that by reading either an A or a B, then by reading any number of B's, and then by reading an A. So what I'm going to do now is I'm just going to cut this state out, and I'm going to remove these transitions, okay? And I'm going to add these 2 transitions because they exactly preserve the information, or they exactly preserve the control mechanism that 2 was offering for 4 to get to 3 and for 1 to get to 3, okay? Excellent. So I do that. Now I have this machine. Now remember, my goal is to remove all states except the start state and the single final state. So now what I need to do is I need to cut out 4. So what does 4 actually allow me to do? It allows me to go from 1 to 3, right? So I can go from 1 to 3 either directly with this guy or via 4 by reading a B and then by reading B, B star A, right? So what I can do is I can cut this guy out, cut this state, cut this transition, and I can say that I can go from 1 to 3 either by reading this guy or by reading B and then B, B star A, okay? So then I get this as the final GTG. It doesn't have the form that I was really looking for, right? So it doesn't have this form. But what you can just assume that these transitions have empty set regular expressions, right? And so that just means that there is no pattern that allows you to go back from this state to itself, right? And so the only regular expression that's equivalent to this machine then is what's left in this transition, right? And so then the equivalent regular expression will be this guy here, okay? And so that's how you start, right? That's how you start with some FA, which accepts some language, right? It might be at first a bit difficult to know what language is accepted by this FA. And so that's why this is sometimes useful, because now when I look at this regular expression, I can see, oh, well, the strings accepted by this FA, they're either, at least 3 B's, then ending with an A, or either an A or a B, starting with an A or a B, any number of B's, and then ending with an A. So actually, it's anything that ends with a B, and then that starts with either an A or a B, is followed by any number of B's, or has at least 3 consecutive B's at the start, right? So that's one of the nifty things about regular expressions, is that they allow you to compactly denote what the language accepted by some machine is, right? So I encourage you to do this exercise, right? It'll actually be quite useful to practice this conversion algorithm. But lastly, what I want to say is that we've essentially created a new equivalency, right? So we've seen that, right, so far, what we've seen is that the family of languages accepted by NFAs is exactly equal to the family of languages accepted by DFAs, which by definition we said is equal to the family of regular languages, okay? And so what we've just shown is that for any regular expression R, there is an equivalent machine M, and for any machine M, right, of course, these machines have to be FAs. For any machine M, there is an equivalent regular expression R. So that means if I have the family of languages denoted by the regular expressions, then there's a one-to-one correspondence between the languages denoted by these regular expressions and the family of regular languages, right? So namely, this means that every regular language has a regular expression that denotes it, And every regular expression denotes a regular language. And so what this means is that we've added to our toolkit of proving L is regular, the regular expressions. So now to prove L is regular, we can either create a DFA that accepts it, create an NFA that accepts it, or now, because of this result, write a regular expression that denotes it. Okay, and so this is a nice result because it allows us to, for instance, if I have the language a n greater or equal to 0, I can spare myself writing the actual FA, and I can just say, well, this is clearly denoted by, say, the regular expression a star, right? So this is regular, right? This language is regular because this regular expression denotes this language, right? Because this language contains strings that start with an A and then are followed by a sequence of BAs. And this is what the pattern that's identified by the regular expression is. It says, I'm looking for something that starts with an A and then is followed by any number of BAs in a row, right? And so this is a nifty final result related to the regular expressions.